Okay. Get slightly distracted there for a second. Right. I'm going to do it the long way. This is not how you would necessarily need to do it. Here is 0. Here is a half pi. Over here is pi. And finally, this is 3.5 pi. The problem that you've got here is that this guy is not a multiple or a fraction of pi. It's not 4 pi. It's no 4/7 pi, right? It's just 4. So the first thing I have to do is figure out exactly where that guy is, right? Is he in the first, second, third, or fourth quadrant? So what I'm going to do is I'm going to take these 4 key places and I'm going to rewrite them as their decimal value. Well, 0 is 0. A half pi on my calculator at least, and I don't need to be too precise, I'm just going to use 3.14. A half pi is about 1.57. Pi is 3.14. 1.5 pi. Now, if you want to be more accurate, just use your calculator pi and it'll give you like 4 or 5 decimal places. But right now, this will do. So you might say, well, why are those numbers going to help me? Well, here goes. I want you to think of a very weird clock that didn't go all the way, you know, the usual way, but it starts at 0 and it finishes back here at 2 pi, right? Which I guess I should put in, which is 6.28. Now, where does 4 go? Can you imagine a clock hand turning? 1.57, 3.14, 4.7. Oh, it's not going to get any further. I now know what quadrant this fella's in. That's, I don't need to be accurate about it, that's roughly where t equals 4 would go, right?
Okay.
Now, the reference angle is always the angle that you make with the x-axis. In this case, it's that guy. And I'll just use the notation, that way I don't need to write the word reference angle. That thing means reference angle. All I need to do is figure out how to get his value. Well, 4, right? Add or take away pi. What do you think I'm going to do? What calculation? Is it going to be 4 take away pi, or is it going to be pi take away 4? How will you find this distance? Well, say to yourself, which is the biggest? Because that's the guy that's going to go first.
Yeah, the 4, right?
Yeah, so it's going to be 4 take away pi. And I believe that's what they want, not the decimal version of that, but just the 4 minus pi.
Okay, that makes more sense.
Are we good? Michael, have you got anything for me? Any questions you want me to go over before we look at
yeah, just quickly on that reference number for each value, like how negative 11 pi over 13.
Okay, we could try that one. I'm going to move this to a new piece of paper, so maybe writing big, but that's fine. So we have an angle negative 11. What was the bottom? 13?
Yes.
Okay. Well, the way I would tackle this question is that I need to know what quadrant it's in so I can draw the picture and put it in the right quadrant, because once I've done that, I'm pretty much done with this question. This is a negative one, so I'm going to add 2 pi to it. So that's negative 11/13 pi, add 26/13 pi, and that gets me 15/13 pi. I want to get an angle that's somewhere between 0 and 2 pi, because that way I can put it into my unit circle, right? My little table thing that goes like this. Now here's 0, here's a half pi, here's 1 pi, here's 1.5 pi, and I guess back to here, here's 2 pi. Now, this fella, which quadrant's he going to be in?
Well, I guess it's over pi.
Right.
Would it be in, I mean, I just guess quadrant 3, but I'm not sure.
You're right, it is quadrant 3, so let's try and make it so that it is less of a guess. And we'll show you how we would do that. Right, so this is the t, this is where for 15/13 pi is. Right. If you take 15/13 pi and you rewrite it as a rough decimal, just by going 15 divided by 13, you get about 1.15. Now, this guy here, he's basically 1 pi, and this guy over here is 1.5 pi. Do you see that it's between here and here, and that guarantees it in the third quadrant?
Okay, yeah, that makes sense now to me.
Right, so all those weird fractions that you're going to get, you know, the 17/11ths, the 22/15ths, and all those guys, if you just do a quick division to find out what the decimal is, you should be able to place it into one of the 4 boxes, one of the 4 quadrants. Now, that's what I think.
I answered that one, and for the reference number, it said the answer was 2 pi over 13.
2 pi. Okay, let's see why it is then. Right, do you know this little bit, the angle that your guy makes with the x-axis? That's the reference angle. That's what they wanted you to find. The guy that, the 15/13 isn't the final answer, it's just the guy I need to get the final answer. Right, so let's find what the reference angle is, the angle that this fella makes, this line here, makes with the x-axis, this shaded red guy. Now, that's pi, and that's a little bit bigger than pi. So the difference between these two is what I want. So that's 15/13 pi, take away pi. 15/13 pi, take away 13/13 pi, and there's that 2/13 that you were talking about.
Okay. That makes sense.
Okay. Right, next, well, I don't know what next is, as I know what I'm going to do, but I don't want to use your time up on something that you'd prefer me to do instead. So what do you have next for me?
Could we do t equals -7 for the reference number?
Now, this is similar to the other question. We're going to find what angle this weird-looking guy makes with the x-axis. But you notice he's another one of those, it's a number, not a multiple of pi. It's not 7 pi or 3/4 pi or anything, it's that fella. So that's going to cause me a little bit of a problem. The first problem we're going to have is I need to know which quadrant he's going to be in. Now, this guy is 0, which is true. This guy over here is a half pi, but I'm going to turn this guy into a decimal, which is 1.57. This guy is pi, but I'm going to turn him into a decimal, 3.14. This guy here is 3/2 pi. Again, I'm going to turn him into a decimal, 4.71. And then if you go back to the beginning again at 2 pi as a decimal, 6.28. Now, anytime it's negative, what do you do to this guy to get it into the place you need it to be? You need to get it to be positive, right?
Yes.
And so what do we add to a negative angle to try and make it positive?
Would be 2 pi.
Okay, so I'll try and add 2 pi to it. Well, -7, add 2 lots of 3.14 is -7 plus, what would that be? 6.28, which ends up being -0.62, roughly. Now, I can skip a little quick thing here. Do you know that if you go backwards, -0.62, you get to this guy here? Or I would simply just add another 2 pi and get that number, which would take me to the same place. I'm just trying to cut down on my workload. You know, like negative a third pi is the same as positive 5/3 pi, right? Negative a third add 2 gets you there. Now, what we are after is this guy here. Well, I can use another little cheat on this one. See this guy here, this negative fella, right? Isn't this angle here 0.62? Because we're talking about the angle it makes with the x-axis. So from there to there is always going to be a positive number. You never get a negative answer in the reference angle. So I know that if you're going this way, we call that negative, then going that way, we would call it positive. So there is my reference angle. Now, if they want it as a decimal, it's 0.62. If they want it as an exact value, then I have to do a little bit of working, and I have to go up here, and I have to say, you know, if you did 7 take away 2 pi, you switch places. You've got a positive answer instead of a negative. And so that's one way of doing that. Just showing you a different approach to that kind of question. If you want to do it as the way I showed you the previous question, it will work out exactly the same. It will just take you like a bit longer to do and a little bit messier numbers, but it will eventually be 0.62 or as an exact value 7 take away 2 pi.
Okay, so if the homework or the quiz doesn't ask for a decimal value for a question like this, you just give it
must be exact. Yeah.
Oh, okay. Yeah,
right.
that's
So if it doesn't say decimals, you need to go exact. If it does say decimals, then do it. That's
okay.
That's the rule.
Awesome. Thank you.
Michael, you got any questions?
Yeah.
Sure.
My question was on the 5.2.
That's fine.
Let's see here, I wrote it down. It says, write the first expression in terms of the second if the terminal point determined by t is in the given quadrant.
Okay, so what I'll tell you what, I can actually, if you hold on a second, I will go in and find the equivalent to that question.
Okay, it's question 13.
Right, hold that thought, 13. And give me a few seconds. I don't think you can see anything right now, but basically I'm just loading up our thing. So it's section 5.2. Once I get it, I'll come out and then I'll share the screen. So view it. Open up a little bit. Question 13. Gotcha. Right. Now the version I've got is the cosine of t, and it's to be written in terms of sine t. What was your guy?
That's the same.
Same one. Okay. So we have a cosine of t, and we want to write it in terms of sine t.
Yeah, in quadrant 3.
Oh yeah, quadrant 3 actually is more important than you might think. Okay. First thing I'm going to do is I'm going to write down an identity that has cosines and sines in it. It's this guy. Are we okay? Is that what you're saying? You saying this?
Yeah.
Okay. So what that is going to do, it is going to allow me to write cos squared as 1 minus sine squared. That's not quite what I want, but it's closer, right? I want to take cosine t and write it down in terms of sine t. But what I've got here is cos squared t, and it's in terms of sines, which is kind of halfway there. What would I do mathematically to both sides if I wanted to get rid of a square of something?
Square root.
And what a lot of people, unfortunately, hopefully you're not one of them, forget is that when you take a square root of both sides, there's actually two possibilities. Okay? Like if you do x squared is 9, x could be plus 3, but it also could be negative 3, right? You're taking the square root. Now, this quadrant 3 is going to come into play. Little baby, all sine tan cos thing. In the third quadrant, which is in here, right? Is the cosine positive or negative when it's in the third quadrant?
In the third quadrant, I want to say it's negative.
You're correct. All first quadrant, all of them are positive. Second quadrant, only the sine is positive. In the third quadrant, only the tangent. Well, if only the tangent and its partner cotangent, but only the tangent is positive, that means the other two sines and cosines are negative. So you're right. It's negative, which means the square root that you choose is the negative one. The cosine is negative in the third quadrant, so we pick between these two and we pick the one that's negative. If they'd said up here, quadrant 4, right? Same question, write cosine in terms of sine, right? Here's cosine using the sines, that's that done. But in the fourth quadrant, it's this one here, isn't the cosine positive?
Yes.
So this would be exactly the same. All I would do is change this to a positive. So the quadrant that they give you in these kinds of questions has one job. It's to tell you whether your answer is going to be plus or minus when you're finished. Because sometimes you do them some numbers and you get the cosine of t could be plus 3/4 or it could be negative 3/4, right? You know it's 3/4 because the math and the numbers tell you it's 3/4. But what you're not sure is it's a plus 3/4 or a negative 3/4. That bit you get from the quadrant that the angle is in. So if it was in the first quadrant, cosine would have a positive number, 3/4. If it was the third quadrant, it would be called negative 3/4.
Okay.
Okay.
That
Let
makes
me show you a numerical version of this question. Suppose I tell you that the cosine of t was negative 3/4, and I told you that t was in the third quadrant. And I asked you to find the sine of t. So you might have even seen a question not unlike this one. So show you how I'd approach that. I'd begin with this particular piece of information, which is really useful for many of these types of questions. And I'd say, okay, that means that the sine squared of t is the cosine of t, which is negative 3/4 squared. And when you add them, you get 1. That makes sine squared of t plus 9/16 equals 1. Then I just keep going a little bit further. Well, if I subtract 9/16 from both sides, and if you take 1 and subtract 9/16, you're going to, trust me, I believe, you get 7/16. And now I need to find the sine of t. So what should I do to both sides if I know sine squared is 7/16? What should I do to get sine t?
You'd find this, do the square root.
Right. But when you take a square root, you get a plus and a minus, don't you?
Yeah.
Now, in the third quadrant, remember our all sine tan cos chi. In the third quadrant, which is
that 7 supposed to be a 9? Right. It didn't just.
yeah. The reason it's 7 is 1 take away 9/16
Oh, okay.
leaves you with 7/16.
Okay.
So my question is, what is the sign in the third quadrant, positive or negative?
Negative.
So that's why it's going to be this fella. Now, although this is the answer, that's not the one the book's going to, or the software is going to accept, because we consider this kind of bad form. So the next few lines are me just making it look pretty. It's going to be the square root of 7 on the top over the square root of 16 on the bottom, which becomes the square root of 7 on the top over 4 on the bottom, and that's the answer they would be expecting to see.
Okay. Yeah, I handled those somewhat differently.
Oh, there's more than one approach to these, so that doesn't mean it's wrong. It just means you're using a different approach. As long as it's
good to know
the
that.
correct approach and it works, it's fine.
Yeah.
Then you're good. Right. Okay, let's spend a little bit of time, what we've got left, 20 minutes, on talking about transformations of functions. So if you bear with me for a few seconds. If you go to Canvas, you'll find that there's a program that I've got, but I've given you a reference to, which is an emulator for the TI-84. So if you do not have a TI-84, and it's kind of helpful for a lot of the graphing questions. So when you get to section 5.3 and they're asking you to look at transformations of sines and cosine functions, it's very helpful if you have a calculator like a TI-84. So if you haven't looked at that, go to Canvas, it's on your front page. There's a link, you get a 90-day free trial. So I suggest if you don't have a calculator, they might want to take up on that. And that's what I'll be showing you right now. Now I've got it set up. On Thingy-Bob, I forgot what you call it, but I'm going to put it on share screen. And here it is. So no, have you seen this guy yet? Is this news to you? Either of you, have you seen this?
I have a TA.
Then you're good. You don't need to worry about this at all. But this will show you how to do it.
I also have a TI-84 too.
Not a problem. The good thing about me is I can still show you what I'm doing on this, and you could imagine doing it on your physical calculator, which is cool. Right, so I'm going to make sure that the mode in this particular case is degrees, which it is. But quite a lot of questions are radians, so if you ever need to be radians, make sure that you do that. One of the most common mistakes is that you have it in the wrong mode. And so you do it, and then you look at theirs and you say, oh, it's not right. It doesn't agree. So make sure it's radians when it should be radians, degrees when it shouldn't be. And I'm going to go in and I'm going to start with a very simple function, the sine of x. And do a window. That's a good window, actually, 0 to 360. Let's just pretend that the 0 to 360 wasn't any good, so you just type it in, right? Make it 0 to 360. Seems reasonable for us. A trig function, right, from 0 all the way back to the end. And I like to use what's called zoom 0. That way I don't need to worry about what these numbers are and play about with them. So if you hit zoom, there's a whole load of choices here. There's another one just out of sight here with a 0 beside it. So I call it zoom 0. It's actually zoomed to fit. And what you got there is a perfect sine function. That's what it looks like. And if you think about it, the sine of 0 is 0. This place here is a half pi where it reaches the value of 1. So the sine of a half pi is 1. This here has an x value of pi. Sine of pi is 0. If you get to the sine of 3 halves pi, it's -1. And if you get to the sine of 2 pi, it's back to 0. This is one complete cycle of the sine function. If I go and I take this window and I double up to, say, 720, and I graph it again, can you see that what the sine function does is it just repeats itself? And in this case, the distance from the start until it gets back to the same starting point, which is here. So this guy here would represent just one cycle. That's called the period of the trig function. So for the sine and the cosine function, sine x and cosine x, the period is 360 degrees. So we would look at this and we would say this is 2 cycles. The period is 360. Now, a couple of other terminologies that you'll be used to. See the height that this thing goes up to, the biggest height, the biggest y value, and obviously in this case the biggest negative value. This is called the amplitude. In this case it's 1. So let me put on top of that the cosine function. And we'll keep the windows the same, that way we can compare them. When you look at the cosine function, it's got pretty much the same shape as the sine function, but it's slightly out of sync, we say out of phase. So if you're into electronics and you look at sound waves or just physical waves, for instance, they all have, this shape that, one sound could be slightly out of sync in the other, right? That's a term you might have heard. So what makes the cosine different? Well, the sine starts at x equals 0, the sine is 0, but for the cosine, at 0 radians, the cosine is worth 1. But they follow each other in perfect harmony for the end of the universe. Now I'm going to go back here and we'll just focus on, let's focus on the cosine this time. So I'll just show you who he is. There's the cosine. I'm going to go to the window and take it back to 1 cycle. That way there's not too much happening. There's a pretty interesting curve. It's what the cosine looks like in 1 cycle. And now I'm going to do some transformations. I'm going to take the cosine of x and I'm going to add 3. Now from 141, if you take a function, x squared or whatever it happens to be, and you add 1 to it, doesn't the graph of that shape now change in some way? We call that a transformation. How would you describe this particular transformation? What do you think this is going to do?
I think it's going to go up 3 units.
Sounds good to me. So I'm going to do zoom 0 so it can accommodate. That looks to me like it went up 3. Now, just for completeness sake, suppose it was subtract 2. It should go down 2, right? Zoom 0. Doesn't the blue guy look like the red guy has been moved down 2 to get to the blue guy? Works perfectly fine. Now, let's look at some other transformations. Let's suppose you change the amplitude. Remember, the number is how high up it goes? And the amplitude's always a positive number. So if I do 2 cosines, what do you think that's going to do to the shape?
The 2 should stretch the graph.
Mm-hmm. Michael, do you agree with that? Do you think the 2 is going to stretch this cosine so the y values are twice as big as they were before?
Yeah, I agree.
Yeah, I agree as well. And let's just verify that. Now, the red one is the original. Do you see that the blue one at any given place, it's now twice as high as it was? Now, that guy there is the same place, but 2 times 0 is still 0, right? So that's totally okay. Now, I won't go through the next one, but if I change the 2 to a half cosine x, wouldn't that have the effect of a vertical shrink of a half? Right, 2 cosine x, vertical stretch. A half, vertical shrink. Right? But this one, how about this one? And I'm going to use the negative symbol, not the subtract, they look very similar, but the negative symbol. So this is negative cosine x. Now this is definitely a reflection. But there are two axes it could be. One of them could be the x-axis, one of them could be the y-axis, right? Which one is negative cosine x going to be a reflection in?
Going to reflect across the x-axis.
Right. I agree. In layman's terms, we'll turn it upside down, right? Should work. Looks like a reflection in the x-axis to me. Perfect. For completeness sake, let's do the other version then. So I'm clearing this guy out. And the other version is a cosine, but the negative is what I call on the inside, right? It's inside the cosine, right next to the x here. Now that's what a reflection in the y-axis looks like. There is a little bit of a problem with visualizing this. So I'm going to open up my window to be negative 360 and positive 360. That way you can see the y-axis and hopefully you'll see the reflection. There is another problem, which you're going to see right now. Did you notice that just for a few seconds, the blue function went first, and then the red function, the cosine of negative x, went right on top of it? Can you see what has happened is that if you take this red shape, which is the cosine function, if you reflect it in the y-axis, don't you get the same guy? So you can't see anything happening here because both graphs are on top of each other. And what that is telling me is that if you take a cosine function and you reflect it in the y-axis, it's the same guy that you would have that you started with. Mathematically, that's the cosine of negative x is equal to the cosine of x. I think it's called the odd-even property you might have seen floating around. Right, so we've done left and right. Sorry, we haven't. We've done up and down. We've done vertical stretch and vertical shrink. We've reflected in the x and we've reflected in the y. There's a couple more that we have still to do. This next one is going to be a movement left and right. Now in 141, you would have x squared and then you'd have a guy called x minus 30 squared. And that is a transformation. And it's a movement of the original cosine function, but you either move it to the right 30 degrees worth or you move everybody to the left 30 degrees worth. Which one is that, fella?
That one should move right 30 units.
Okay. Michael, what's your opinion on that?
Yeah, right.
I agree. I agree. I'm going to go back and just adjust my windows again. And now I'm going to do zoom 0. There. The red one is the cosine function. Okay? You see the red one's the cosine. Can you see what's happened to the red one? If you shift it to the right, don't you get the blue one? Can you imagine, you know, this guy, this high guy is now there. Right? You might say, well, what about this piece here? This piece here is coming from the bit that used to be down there. Right? You know, it's like an infinite piece of string. So you get to see more than you want. And so you notice that they don't finish at the same height. If I continue this, maybe I should, just a little bit. If I continue this for a couple of cycles, you might see it a little bit better. Yeah, can you see it? The blue one is in front of the red one by 30 degrees. We call that a phase shift. So that's going to be the jargon that you'll see when they ask you questions. The phase shift is 30 degrees. Positive 30 degrees, meaning it's moved to the right 30. Now, if I go back and we change this story, and we make this fella here positive 45, shouldn't that move everybody to the left 45 degrees?
Yes.
Right? So let's see what that looks like. Oops. Here we go. Remember, the red is the original cosine. It's hard to keep track of who's the original. Red is the start guy. Can you see the blue guy has now been shifted to the left? We'll assume 45 degrees. So if I take a point like, you know, wherever that hill is, this hill is like 45 degrees to the left of it, right? 45 on the x-axis to the left of it. Make sense? Right. Now, we've got time for a few more transformations. How about, this is a new guy. Really, you don't spend much time, if any, in 141. So we can't really use our 141 knowledge here. So I'm just going to show you what it looks like. And I'm going to take my window and reduce it back to the standard position. And now we're going to graph it. Now, the red one is the original cosine function. The blue one is the cosine of 2x. Now, what you might notice here, and I hope you do, is, do you notice it's got basically the same shape, but it's being compressed in the way? So it's like a horizontal compression. If you look at it in another way, isn't there two cosine worths of shape in that one window? Can you see it goes up and down 2 cycles worth? So if I did the cosine of 3x, what I should expect to see is the same basic cosine shape, but a lot more compressed. In fact, compressed in such a way that you get 3 cosine shapes inside that window. So here goes. Trust me, that's 3 cosines worth. Right. So that is a horizontal compression. So a sine of 2x would have 2 cycles inside 0 to 360. A sine of 10x would be zooming up and down like a yo-yo, because a sine of 10x would have 10 sine functions. Imagine the sine shape, 10 of them crushed in a 0 to 360 window. Or if you do radians, a 0 to 2 pi window. Well, what's the alternate look like? Well, suppose I'm going to use 0.5 because it's easier in the calculator than trying to do a half. If a cosine of 2x gets you 2 cycles, then what's a cosine of half x going to do?
Should stretch it.
Yeah. It should stretch it by a factor of 2, in fact. A half gets you twice. Now, what does that look like? Well, when you graph it, it's going to look kind of weird. Do you see the blue guy is only showing you that much? So I'm going to open the window to 2 cycles of a normal cosine. And what you'll see is the cosine, right, the normal red cosine, gets to do 2 cycles, and this poor guy only takes 1. So when you look at horizontal stretch or compression, right, that's a stretch, right, the thing's getting stretched out. One of the ways to look at that is to use the period as a way to help you understand it. The period of this new curve, the blue one, is 720 degrees. If you looked at the x value here, it would be 0. And if you looked at the x value at the end of this line, it would be 720. It takes 720 degrees to repeat itself. And so there's a distinct mathematical connection between sines and cosines of 2x's and 3x's and a half x's and a quarter x's. And the connection is the periods of those functions change because of the coefficient of x. So for instance, see if you're a sine of 2x, your period is only 360 divided by 2, 180 degrees. If you're the sine of a half x, your period is 360, but you divide it by a half, which gets you 720 degrees. And that's all we have time for today, because I have another Zoom meeting to go. Or, as always, if there's any issues, you shoot me an email. If it's something I need to do visual, we'll set up a Zoom meeting. So it was nice seeing you guys, and I'll see you tomorrow. No one.
Yep.
Yes, I will
Thanks for
tomorrow. Okay,
Sounds
bye-bye.
good. Thank you.
You're welcome.